Yogah Karmasu Kaushalam.
The title of today's refresher talk is Digitization, Number Systems for Counting to Generate Binary Digital Output. The process of digitization is converting any analog signal into a digital number. By digital number, we mean a binary digital number, and we want the output in terms of only two symbols 0 and 1, that is called a binary system, number system. We are familiar with a decimal number system where we have got 10 symbols 0 to 9, and if we want more numbers, then for the counting process we have to use a carry, so tens, hundreds, and so on and so forth. Now in the digitization process, what we have to do is analog voltage is converted into a digital number which is equivalent to that voltage, and for that purpose the binary digital output number has to be obtained from a given analog voltage. Now this process of digitization is nothing but a counting process, and for that we require digital counters and other circuitry which we will study in this talk. Similar to these digital systems, another system is time measurement system. This is also a kind of a man-made activity. We want to measure time, and the time is measured since lakhs of years. The earth is rotating about itself. The uh, moon is revolving around the earth. The earth is revolving around the sun in 1 year, that is 365 1/4 day, and the solar system is moving towards some galaxy. So in terms of those cycles, we try to make the measurement of time, number of cycles. But these cycles are not very constant. Some aberrations, some changes take place when some huge objects come near the earth, and therefore this time measurement is not as exact as number system. Yet another human activity is language. Language, in English language we have got A to Z 26 symbols, and in terms of those symbols we try to convert them into words, and then we try to combine the words to make sentences. We combine the sentences to make paragraphs and try to express ourselves. But this system is a human made system, and English language unfortunately is not a phonetic language. So PUT, put, and BUT, but. So the pronunciation of U in first case is U, PUT, and in another case it is but and put. Therefore, the pronunciation is different of the letter U. So it is not mathematical and precise. And some sentences, some combination of words only will make meaningful sentence. Otherwise, it will not make meaningful sentence. So in order to communicate with each other, man has made languages, and this is a totally human made activity. But we understand that for digital systems, the best language on the earth is the Sanskrit language. Since thousands of years, this language is in use, and we have got 12 vowels, that is a, e, u, a, I, o, aha. These are the 12 swars, and vyanjans, that is consonants, we have got k, k, g, and these are 36 numbers. So 36 into 12, 432 is the total number of symbols available to us, and in terms of those symbols we try to make words, languages, and this language is most mathematical and precise language. The grammar is also very precise, and therefore it is said Sanskrit is the best language for use in computer. Dear friends, today we are trying to study what is analog to digital converter. The process of converting analog signal into digital signal is called analog to digital converter, ADC. ADC is a circuit which accepts the unknown analog input and converts it into n-bit binary number. It represents magnitude of the input analog signal. This is a block diagram of a ADC. Analog input voltage is applied at this point. This is the analog to digital converter, and at the output of the ADC we have n-bit digital number. Digital binary number has got only two values, 0 and 1. This is the block diagram of a ADC. At the heart of the ADC is a comparator, which is given an analog input voltage, and to the other leg of the comparator we give an input which is coming from a feedback system. Comparator output is applied to a binary counter. This binary counter is a digital counter IC which goes on counting from 0000 to 1111. And what it counts? It counts the clock pulses. A clock is a circuit which produces square pulses which are either digital 0 or 1. These are also applied to the binary counter. And binary counter goes on counting from 0 onwards. But whatever binary counter number is available, that number is a digital number which is applied to a latch. Latch is nothing but a temporary memory, and this is a digital memory which stores either 0 or 1 and gives at the output the digital number. And the binary counter, whatever number is stored in the binary counter, is applied to a DAC. DAC is digital to analog converter, which is the reverse process of ADC, and this digital number is converted into analog voltage and applied to the other leg of the comparator. So comparator output is a digital output, either it is 0 or 1. Digital to analog converter DAC and its application. DACs are in many cases a part of ADCs. These are used in the feedback path of the ADCs. Reconversion of digital to analog is essential in many industries to obtain signals for controlling the processes. Many equipment like motors, plotters, various parameter controllers like heaters, coolers, etc., in general actuators require analog signal inputs. This is a very important application in the industry for DACs. Astable clock pulse circuit, 555 monostable pulse circuit, comparator circuit, 4-bit asynchronous simple counter, DAC R2R ladder circuit, sample and hold circuit, AND gate operation. Now these different blocks together make a system which is an ADC. IC 555 can be used as a astable clock pulse circuit by connecting three external components, two resistors and one capacitor. Schematic of IC 555 as an astable multivibrator with external components is shown below. This is a IC 555 of 8 pins. A capacitor is here, two resistors are here, and by the use of these components we are able to get at the output square wave pulses. These type of pulses are available. The charging and discharging of a capacitor from 1/3 VCC to 2/3 VCC. This is the charging, exponential charging, and this is exponential discharging that continues, and corresponding to this we get a time on output high and time off output low. These kind of square pulses are generated by controlling the charging and discharging of the capacitor. Duty cycle is a mathematical parameter that shows a relation between high output and low output. Duty cycle D, T high divided by T high plus T low. Charge time T on Tc is equal to 0.693 R1 plus R2 into C, and while discharging T off Td is equal to 0.693 R2 into C. Percentage duty cycle is given by percent D is equal to 0.693 R1 plus R2 into C divided by 0.693 R1 plus 2 R2 into C into 100. So D is equal to R1 plus R2 upon R1 plus 2 R2 into 100. The frequency of oscillation can be calculated as F is equal to 1 by T is equal to 1 over 0.693 R1 plus 2 R2 into C, that is 1.44 R1 plus 2 R2 into C hertz. This is the type of frequency that will be generated of the square wave pulses. This frequency is 1 upon T. Now a stable clock pulse circuit. With this 555, different types of capacitors are used and they are switched one after the other, so you can get a very large range of timing available in the circuit. This is that IC 555. These are different capacitors which are switched one after the other, and this is the type of output that is available from the circuit. The A-stable multivibrator is used as a timing oscillator or a clock for a computer system. It is also used in power supply circuits, flashing lights and switching. In radio gears, it is used to transmit and receive radio signals. It is used in generation of Morse code, timers and a pulse train. In some systems, we require a square pulse train, analog integrated circuits and television broadcast. It is used in applications like pulse position modulation and frequency modulation. These are various applications of IC 555. Then IC 555 is also used as a monostable pulse circuit. Means only one state is stable, other state is quasi-stable. So you move from one state of the output to another state, and when it is at quasi-stable state, it automatically jumps back to the first state, that is the stable state. The monostable pulse circuit includes two extra components resistor, only two components, resistor and capacitor. Monostable multivibrator has one stable state. Time duration for which pulse is high will depend upon the timing circuit of resistance and capacitance. This circuit is shown over here. Pulse width derivation. Pulse width is depending upon T divided by RC. So T is equal to 1.1 into R into C, so that the pulse width of the output rectangular pulse is given by W is equal to 1.1 R into C. The time for which output stays high is controlled by the timing circuit of one resistor and one capacitor. Width of the pulse is also controlled by timing circuit. So we can say that charging time of a capacitor is depending on the time constant RC. This is the trigger of a sufficiently large voltage has to be applied, then the circuit will go into a high and remain high for a limited time T on, which is 1.1 into RC. So from 0 to 2/3 voltage it gets charged capacitor, and then it is again discharged suddenly. This is the circuit, and these are different capacitors which can be switched in, one resistance and a potentiometer to adjust to any particular value, and thereby we are able to get a large timing available for doing the experiment. Applications: frequency divider, pulse width modulation, linear ramp generator, switching on the relay, missing. Comparator is another important circuit in ADCs. The comparator has two input terminals and one output terminal. The two input terminals are analog input voltage VA and a reference voltage input terminal V reference. The digital output is V0. Comparator compares the two input voltages and produces a digital output either 0 or 1. So input is two analog voltages or any voltages and output is either 0 or 1. So this is input voltage, this is a reference voltage. Compared to reference, it is given, this input voltage is given to a plus terminal. So compared to reference voltage, if this voltage is high, you will get a high output. If this voltage is low, you will get a low output because it is applied to plus. If it is applied to negative, then reverse effect will be there. And to run this comparator, it has to be powered by plus minus VCC, because on the negative side also you can have a output and plus. So you need a dual power supply for a comparator. This is the hysteresis type of diagram of a comparator output. Now another important circuit used in ADCs is simple counter. Here we are discussing a 4-bit asynchronous simple counter. Counting is most common requirement in digital system, and most common counting requirement is to count with time. So we want to count pulses. 4-bit simple counter can be constructed using clocked JK flip-flops. Figure 15 shows 4 JK flip-flops connected in cascade. One after the other they are joined. This, this is the clock applied. The output of the first flip-flop goes as a clock to the second flip-flop. The output of the second flip-flop goes as a clock to the third flip-flop, and output of the third flip-flop goes as a clock to the fourth flip-flop. And therefore these are in series, so their uh, timing is also asynchronous, and they can count from 0 0 0 0 to 1 1 1 1. So you can start from 0 and count up to 16. So there are 16 levels and a 4-bit up down counter IC using IC 4029 is this IC. The inputs are can be switched from here zeros and ones, and accordingly the output will be produced. Another way of producing output is apply push button, and from push button you go on applying pulses, and those pulses will be counted, and these 4 LEDs will show you 0 0 0 0 to 1 1 1 1 how the counting progresses to give you the. Then another important circuit is digital to analog converter for the feedback, and this kind of a converter requires R2R ladder network. The DAC R2R ladder circuit is basically variable resistor network which is used to change digital signal to analog signal. For this, n voltage levels are used in one analog voltage. By designing a resistive network, it will change each level into equivalent voltage or current. So, this is a op amp. One leg of the op amp is connected to ground. So, we are applying different voltages in succession. This is a 4-bit thing. So we can start from 0 0 0 0, go up to 1 1 1 1, and accordingly 16 different voltages can be applied to this system, and this is a feedback resistor, and the output is available over here. So this R to R ladder network, 2R ended by 2R, then R, then this is ended by 2R, this is R, this is 2R, this is R, this is 2R. So accordingly you can go on indefinitely, as many number of bits you want you can apply here. So this ladder network is a very important network in DACs, digital to analog reverse conversion. Now we have used DAC 0808 for converting analog signal into digital signal. It is used for converting 8-bit digital data input into analog signal output. 8-bit digital data. Its power consumption is low and accuracy of conversion is good. So DAC 80808 is a 8-bit DAC. 8-bit corresponds to 0 to 256 binary numbers, 8 zeros to 8 ones. It corresponds to 2 raised to 8 minus 1, that is 256 levels. You can count from 0 to 255. These are the input pins, and these are the digital inputs and a ground, and this is the output, op-amp at the output, and which will give you a output which is corresponding to this digital number which you have applied. Corresponding to that, you will get a voltage over here. This is a DAC. Accuracy is good because there are 256 levels. So assuming 0 to 1 volt is the range, that is 0 to 1000 millivolts, you will get at every 4 millivolts a step, and therefore resolution is very good. 4 millivolts is equal to 0.4% resolution. 0.4% resolution is difficult to get in mechanical systems. Now another important circuit which is used in analog to digital converter system is a sample and hold circuit. Is used to sample an input signal and hold on till the sampled value is converted to analog to a digital number by the circuitry. It, because there are gates, because there are transistors, because there are switches, all these have to be applied signals, and it takes finite non-zero time for this to happen. And therefore for digital interfacing and pulse code modulation, we need such kind of a circuit. In a sample and hold circuit, the input voltage is sampled at a point of time, instant of time, and then this is a CMOS. Fast switching transistors are used, capacitors are used to hold the voltage and applied to a op-amp, and the output is a kind of a digital output is available. Sampled analog voltage at a given point in time. So this is the continuously variable analog voltage, and you have sampled it at certain points in time and held it constant, and with respect to that constant voltage you are getting a level. So square pulses are generated. The input is analog and output is square pulse. That is the job of a sample and hold circuit. Now types of analog to digital converters. Based on conversion methodology, common types of converters are flash or direct conversion or simultaneously conversion technique. This is the fastest. Then there is a counter type ADC which is very slow. Successive approximation ADC comparatively faster. Integrating type of ADC, single slope and dual slope or multi slope ADCs, which are extremely slow, the slowest but most accurate. Then sigma delta ADC, again very slow. Simple counter ADC is slow, and then sectional counter ADC is fast. So these are various types of ADCs which are available. Now first let us discuss simultaneous conversion method. Introduction. The simultaneous conversion method of analog to digital converter is also known as a flash type analog to digital converter. It is based on a number of comparator circuits. For n-bit conversion, 2 raised to n minus 1 comparators are required. So huge hardware is required. For a 4-bit ADC, 2 raised to 4 minus 1, that is 15 comparators are required. And comparators are important. This is the fastest method to convert from analog to digital, so it is called flash. In a flash, you get the output. One single pulse and the output is available. As many bits as you want. This circuit analysis. Here we are introducing 4-bit flash simultaneously analog to digital converter. For this, 2 raised to 4 minus 1, 15 comparators are required. So you will see other methods where only one comparator will be required. Here we require 15 comparators for 4-bit. There is a voltage divider network. It applies different voltages to different comparators, reference voltages, and then there is a coding network of gates and switches to convert that comparator output into a digital number. And finally there is a LED display to indicate the digital output. Each comparator has a common analog input. The analog voltage which you want to convert is applied to each and every comparator, one leg. And the second input of the comparator is the standard reference voltage which can be applied by R2R ladder network, circuit network, which we had studied just now. Reference voltages used are V by 16, 2V by 16, 3V by 16, like that, 14V by 16, 15V by 16. So 15 comparators will be given different voltages, fixed voltages, depending upon the steps, and accordingly the output will be produced. If analog voltage is greater than reference voltage, the output of the comparator is high, otherwise the output is low. This is the definition of a comparator. In the simultaneous conversion method, these are the 15 comparators, 2 raised to n, 2 raised to 4 minus 1, 15 comparator circuits, each given the same analog input voltage, and depending upon your input voltage, so many comparators will be on. Suppose I apply 9 volts to this, analog input voltage is 9. So up to 9, up to 8, all the comparator output will be high. 9th comparator will be high, and 10, 11, 12, 13, 14, 15 comparator outputs will be low. So this up to 9, all the comparators are high. So you have to convert this 9 comparator high output using digital switching gates or transistors, switching transistors, into a digital number which will read number 9 here. So 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1. This is the outputs available, and this particular coding gates and huge network of this will be required, and first of all 15 comparators will be required. So for 4-bit you can make it, means if you make the circuit it may work, but if you are talking about 8-bit you will require 256 comparators. So you have multiplied by a large number, and then this circuit will also be extremely complex, and that circuit will never work. So unless and until you have a specialized IC to do that, you cannot make small circuits and do it. So that is the difficulty. So simultaneous conversion method up to 8-bit is okay, but more than 8-bit is not possible. Even 8-bit is difficult to make, and therefore you have other techniques to do that. Sample and hold circuit is not required in this method. Complexity is less than other analog to digital converters. It is easy to understand. It is the fastest ADC. Conversion time and propagation time is very small because only one pulse is required. Disadvantages. There are many disadvantages. Hardware complexity increases because of large number of comparators for greater than 4-bit conversion. Now, let us try to talk about another technique which is called counter type ADC. Introduction. Counter type ADC is the basic type of ADC. It is known as ramp type or staircase approximation ADC, staircase, steps. Counter type ADC is constructed using comparator, clock, gate and control, binary counter, and DAC. So DAC is in the feedback path. Circuit diagram of a 4-bit simple counter ADC using DAC in the feedback. So this is the basic counter. Analog voltage is applied to the input terminal VA of the comparator. The other input terminal V reference is applied the analog output voltage of a DAC. So DAC is in the feedback using R2R binary ladder connected in the feedback path as shown in the figure. So this is this schematic diagram. You have a clock generating square pulses, you have a gate and control circuit, and you have a counter, a digital counter. Now heart of the thing is the comparator. Comparator is giving an analog input voltage which is used using a sample and hold circuit. This voltage is sampled and held constant, and then this whole circuit will come into the picture. It will take some non-zero time, convert it and give you a digital output. For that purpose you use CMOS gates and fast switching devices over here to make the things faster, because you will require many pulses to make this counting. Now clock is entering and giving pulses to this circuit, and starting with 0 0 0 0, that is 4 zeros, your counting starts from 0 voltage, and slowly this counter goes on increasing. Suppose we are applying a 9 volts over here, then counter starts from 4 zeros, that is 0 volt. Then the step height is 1 volt in the 4 bit up to uh, 16 volts. Suppose we are applying, so step height is 1 volt. So next step is 1 volt, second step is 2 volt, then 3 volts, like that. The counter will go on producing 0 to 1, 2, 3, 4, 5, and so on and so forth up to 15 pulses it will require to make a 15 number here. Suppose you are applying 9 volts, then up to 9 this counter will go on increasing the number, and after 9 what will happen? Your comparator output will go low because this DAC will produce a 9 volt equivalent here, and your comparator output goes low. It stops the gate, and gate becomes off, and your clock will not reach. So whatever the number in the counter is 9 number, that is equivalent to the 9 volts step, and therefore that is equivalent to analog input voltage. So digital number 9 is available at the output. And suppose you are applying only 2 volts, then only 2 pulses are required. If you are applying 15 volts, 15 pulses will be required. So depending upon the input value of the voltage, less and more number of pulses will be required for this conversion. So this conversion, the output will depend upon the input signal. This is the counter type ADC with a 4 bit. To run these ICs, we will require a power supply. So this is the power supply, and then digital outputs switches are required to start from 000 to 111. This is a digital counter. So signals are given to this counter. The counter goes on counting 0 to 16. This is also counting 0 to 16. So you can think about the 8 bit. So which will go from 0 to 15, and this is a clock pulse generator using IC555, and square pulses are generated applied to the counter, and accordingly you can get a 8 bit output, and you can measure the voltages over here. Circuit details and connections are mentioned in relevant topic. When the reference voltage is equal or greater than analog voltage, the gate will be closed and counter will stop. We get final digital output in the counter circuit for equivalent analog voltage. Now what are the advantages of a counter ADC? Basic. Simple and basic construction of analog to digital converter. It is less expensive and easy to design. By adjusting called frequency, we can adjust the speed of conversion. It is faster than dual slope integrating type ADC, where additional RAM generators are required. Disadvantage. The speed is less than other techniques of ADC. Each time counter will start from a zero, and the next input is sampled. If the next input is sampled before the completion of one process, then it is difficult to show the proper result. So sampling should be sufficiently small. Next method is successive approximation register method. Here, instead of using so many pulses, we are trying to approximate. Successive, approximate again and again. And approximation means using some logic, and register is a register which registers numbers one after the other, counting process. So that kind of a register is there, it is not register. So sample and hold circuit gives a signal, analog signal converted through sample and hold circuit to a comparator. Another leg of the comparator is a digital to analog converter output. So again analog voltage is there, we are comparing the two voltages, and there is a adder or subtractor circuit, and then we are having a control and logic circuit. Here is a ring counter, counter goes on counting, and the counter outputs are available here, binary ladder network, and finally you get a digital output over here. So in the feedback path you have a digital to analog converter, but there is a difference between a simple counter and the successive approximation. Let us try to see what it is. Operation of ADC using successive approximation method. This is the main diagram which we have to understand how comparison is done. We assume, suppose we are applying 4 bit output we want. So from 0000 to 1111. So in the steps of 0 to 16 volts, we are applying 1 volt steps. So 16 steps are required. 2 raised to n minus 1, that is 15 levels are 16 levels are there, 15 steps will be required. 15 ordinary simple counter will require 15 pulses. Here what we do, we assume that we don't know what is the input voltage, so we assume it is halfway through. So we will apply 8 volts at the beginning to the comparator. Now if the output is high, you are in the first half, second half. If the output is less than 8 volts, you are in the lower half. Then if you are in the higher half, you divide this again by 2, so you climb by 4. So first comparison by 8 volts, another comparison by 8 plus 4, 12 volts. If still your output is high, you compare with another 2 volts, you add to it. So 12 plus 2 is 14 volts, you compare. While comparing this 12, suppose the output is low, then you climb down by 2 volts, so you compare with 10 volts. Like that, either in the first case you are comparing with 8 half volt, half. In the second you are comparing either with 12, or if your output is low, you will compare with 8 minus 4, that is 4 volts. So there are two values to compare, either 4 or 12, but which one is decided by whether your output of the comparator is low or high. Similarly, next you have got 4 positions, either high or low. So either you, if you are compared with 12, either you compare with 14 or you compare with 10. Earlier if you have compared with 8, either you compare with 4 or you compare with 2. So that way process will go on, depending upon what you have compared earlier, your next number will be decided either high or low. And finally you will have to have 8 different values to compare for the fourth bit, but any one of them, so one per bit. So first bit, maximum significant bit, one pulse, second pulse, third pulse, and fourth pulse. Within 4 pulses, you have come to the output instead of 16 pulses. So you have reduced the number of comparisons. You have made the system faster. Now for 4 bits, it looks little simple, not much advantage. But when you have larger number of bits, it looks more advantageous. You will see that shortly. We will try to understand this concept through a numerical diagram. This is a numerical calculation to show us how the comparison is made for a 4-bit output. We are doing this with an example. Our input voltage on the x-axis from 0 to 16 volts, this is our input range, and we have, let us say, assumed that analog input voltage is 13.2 volts applied to the system, which is the red line. Now first approximation 0 to 16 volts, so 8 volt is the halfway through. So first input to the comparator is 8, 1 0 0 0, 8 volt is applied. Your comparator say input signal is high, so you 0 to 16 halfway 8, then you have to climb up because the input is high. So between 8 and 16 you compare with 12 volts. 12 volt comparison, again it says the output is high, so you go higher. So now again halfway, so plus 2 volts. So now you will be comparing with 12 plus 2, 14 volts. Now 14 volts, when you compare, that is equal to 1110. When you compare with 14 volts, the output will say you climb down. So you have to climb down 1 volt and come to 13 volts. You compare with the 13 volt, 1101, and after that your 4-bit output is over. So you have made 4 comparisons, you will get the answer 13 volts. Instead of 13.2, your digital conversion will say output is 13 volts 1101. So 4-bit comparison will give this accuracy. If you want more accuracy, you increase the number of bits. So that is an error of 0.2 volts. So in the conversion, the output is 1101. This is the digital output after 4 comparisons, and that is the end of the story. You don't have more resolution, because if you take a example of a foot rule which is marked with centimeters, every centimeter there is a marking, and between 2 centimeters, 4 and 5 centimeters, there are 10 markings of 1 millimeter each. So you can say either 4 centimeters and 3 millimeters, or you can say 4 centimeter and 4 millimeters. You cannot say 3.1 millimeters. That is not possible. That is wrong, because your marking is not available. So you use a vernier, a more accurate thing, you may increase 1 bit. If you take 100 readings and take the average, you may increase 1 bit. But Otherwise, you will need a microscope to go for micro uh, length in terms of micrometers, millimeters, nanometers, and so on and so forth. So you will need more and more bits, your accuracy will improve. Okay. So each bit, the accuracy is increased by half. Now we take another example. If the analog input voltage is only 3.2 volts given by this red line, first comparison again with 8 volts, it will say the input voltage is less, so you climb down by another 4 volts. So you are comparing with 4 volts for the second comparison, and then again the output is less, so you compare with the third, which is 2 volts, 4 minus 2, 2 volts, and then you will come to know the output is high, so you will compare with 3 volts. So comparison output will be 0 0 1 1. So again your output is 3 volts and there is a error of 0.2 volts, which is called quantization error in this system of quantization of a number or digitization of a number, and that error cannot be removed. It can be reduced only by increasing the number of bits. There is yet another technique called sectional counter technique. This technique is used for reducing the total conversion time of a simple counter by dividing. Here we use variable gain amplifier op-amp 741, whose gain is selected by analog switching multiplexer IC 4052. Circuit analysis. The innovation in this experiment is that how the 16-bit ADC is divided into 4 sections of 4 bits each, and how the 4 sections one after the other produce the digitally converted output. This switching of gains of amplifier and switching of sections of the output bits is done by a 2-pole 4-way switch. So let us try to see the schematic diagram of this sectional counter technique. A clock is there, square pulses, it is applied, then there is a gate and control circuit as usual, and the output of this goes to a 4-bit counter. Now 4-bit n lines, level amplifiers, binary ladder, and the output is 4 bits, digital output. Now what is additional here? Analog input is there, which is sampled and hold and applied to the comparator. Now in the feedback path, earlier we had only one DAC of 4 bit. So your resolution was only 1 upon 16, that is 1 volt. Now your resolution is, instead of 4 bits, you will get 16-bit resolution by using 4 amplifiers of variable gain in the feedback path. So this DAC output is also only a 4 bit, but we will have 4 sections: first section, second section, third section, fourth section. So this is the MSB highest section, then the next lower section, then the next lower 4 bits, and next lower 4 bits. So you will try to do this process 4 times with different variable gain amplifiers, and the analog output voltage will be produced by this DAC in the feedback path, and that is applied to the comparator. So we will get the time taken will be, for 4 bits you require 16 pulses. So for 16 bit you will require 16 into 4. So 16 into 4 is 64. So you will require 64 pulses for making this 16-bit output. A normal simple counter would have required 65,000 some pulses. But now your problem is solved into only 64 bits. If it would have been a simultaneous converter, you would require only one pulse. But then in that case, you will require 65,000 comparators, a gigantic thing, which is impossible. Now, if you have used a successive approximation thing, then 16 bits would require 16 pulses and your conversion would be possible. But This is somewhere between the successive approximation and uh, and uh, simple counter. So 4 times 4 bit counters. So 16 per this thing, and 16 into 4 is 64 pulses. So instead of 16 pulses, you require now 64 pulses. Now try to see this circuit in detail. Variable gain non-inverting amplifier for 4 bit. That is the attenuator here we require because it is applied to a negative terminal, otherwise it can be positive. So these are different resistances in the feedback. One at a time it is switched, and accordingly you will get the 4 bit output. Now this will be very clear to us. An amplifier with several gain choices is provided in the DAQ system, digital to analog converter, to boost the lower level signals to optimum level. AV is equal to 1 plus RF by R1, where RF is smaller than R1. Now you see, in the first comparison, MSB, highest 4 bits, first 16 levels are there. So your system is divided into 16. Your output is between 11 and 12, that is the output. So you got that resolution. Then this section 11 to 12 we want to convert. Now you try to see this first section is 1100. It corresponds to the number, right? 11. So 12th section. Now this 12th section, in the second time the amplifier gain is improved, and now you have a 6th section. So out of this 12 we have again expanded it, and the 6th section output you are getting the comparison. So in the third case, in the second case your output will be 0110. Say this is number 6, this is number 12. After that you got a number 6. Then again you amplified that section region to 4 bit, and now your answer is 9. So the third section has given you a equivalent to number 91001. And then this 9 section you have again amplified, and then you are getting a answer between 3 and 4. So section 3 is the answer, 0011. So this way 4 bits, next 4 bits, next 4 bits, next 4 bits are generated by moving 4 times cyclic, and within 64 pulses we have been able to get the output of the digital number, which is a 16 bit output. Full voltage range VA is equal to 0 to 4096 millivolts. Number of bits is 4 and number of sections is 4. So 2357.3110 millivolt is the input voltage. First 4 bits you get the output 2304. The second MSB you get the output 768 millivolts equivalent. The third output you get 1280 millivolts, and the fourth LSB output you get equivalent to 62.5 microvolt. So net answer of the digital 16-bit output is this, and correspondingly you will get a resolution in microvolts. Yet another type of analog to digital converters, a family of them, are integrating type of analog to digital converters. What is the specialty of this? The techniques which we discussed earlier used fast conversion is used when fast conversion rate is acceptable. You are not slow conversion. Here we introduce integrating type of analog to digital converter. It is used where very slow conversion rate is acceptable. These types of converters are slower and useful for measuring slowly varying signals in low frequency and in DC measurements. There are two types of integrating type analog to digital converters: single slope analog to digital converter technique and dual slope analog to digital converter technique. Generally, single slope is only for analysis on and also for academic interest. A comparator is there, there is an analog input voltage, and they as usual there is a gate control and logic circuit. A clock pulses, square pulses are applied to this control and logic circuit. Either the clock is allowed to reach the counter or stops from reaching the counter by this logic circuit, and the counter output is finally a digital output available. And then this digital number is applied to a ramp generator. Ramp generator is a RC ramp generator using RNC. Ramp means inclined plane, so you get a slope instead of steps. Now you get a slope, smoothened steps, and then that is applied as a to the comparator as a input. So this is integration. This is integration means from steps you are making it smooth. So that kind of activity is there, and finally output is available. Now this additional circuit ramp generator will take time because it will use resistance and capacitances, charging and discharging of them, and that will take certain time. Now this is that op amp with respect to plus is grounded, with you are giving a input at the negative through a resistor and a capacitor. So capacitor is the feedback path. So RC time constant, depending upon that you get the output. Slowly varying output is exponential charging function generator. Integrator is used to integrate the voltage for fixed period of time. Suppose input voltage is applied to V in. Output of the integrator stored at 0 volts because there is no charge on the capacitor at initial condition. After integration for a fixed period of time, PO is equal to minus VA T upon RC. RC time constant dimensionally equal to T. So they will cancel, and therefore dimensionally the equation is correct. VO is equal to minus VA proportional to with this proportionality constant. T is the time taken, RC dimensions, and there will be a slope, negative slope because you are applying to negative. If you apply to positive, it will be a positive slope. And then try to see what happens. A single slope technique is the V voltage axis, output voltage, and this is the time axis. So as you go on increasing the time, you have a linear equation RC time constant, this applied input voltage equal to this, and your voltage goes on increasing exponentially, but it should take infinite time to reach the analog voltage because that will depend upon the charge stored on the capacitor, and this is exponential. So ideally it will take infinite time, but the equation is of a straight line having a slope V upon RC constant. This type of converter is low cost converter and highly accurate converter. So for accuracy use this thing. Now dual slope conversion is actually practically used. Instead of a single slope you have a dual slope. Again that RC is there. There is a comparator which gives you a digital output that is converted. These are clock pulses, control and logic circuit. That digital output is available here, and that digital output is applied here, and from the comparator DAC etc. you get a voltage which is applied here, the analog voltage. Now this DAC circuit, dual slope, that RC integrating circuit is here, and that will produce a reference voltage. Now the reference voltage is negative to this polarity. So we are cancelling this R and C in this process. This integrator component R and C will be cancelled in this process, and your output and the referencing and the voltage, output voltage will be independent of R and C components. So these will cancel as constants, and therefore even if you replace the capacitors or resistors, or because of temperature pressure variations, if there are changes in the components, it will not affect the error. So dual slope conversion is used, but it will take double the time because once you have to integrate it in one direction, another time in the reverse direction, and time required will be more, but it will be extremely accurate. So the process is, the output of the integrator is stored at 0 volts because there is no charge on the capacitor at the initial condition. After integration of for a fixed time T1, this is the integration output voltage available to you, and then you have a ramp in the opposite direction, reference voltage is applied in the opposite polarity. So the first time you know how much time you are applied and you don't know the input voltage, but in the second case you know how much voltage is applied, fixed reference voltage, and you calculate the time in terms of pulses available, count them, and that will be proportional to the input voltage. So the derivation of equation is something like this. There are two voltages, one is the input voltage, one is the reference voltage. Reference voltage is known but time is unknown, and here input voltage is unknown and the time is known. So first you apply a fixed amount of time t1, and then whatever voltage is generated will be proportional to the input voltage. Then next time you apply a fixed input voltage, reference voltage, and you allow the ramp in the reverse direction to go to 0. So the time measured will be required. If this voltage is larger, then it will take more time and more pulses will be there, and your digital output corresponds to the input. If the voltage is less, then you will ramp will be saturated very quickly, you will go to 0 and a small number is produced. So V output is again proportional to input with this RC time constants cancelled in both directions. So you can see the way the process is done. Ramp output of the generator is given by this. After reaching up to a fixed amount of time, the counter is reset to 0. Input of the integrator switches to a reference voltage in the opposite polarity. At the time, counter does not start from with 0, 0, 0. It starts with the initial value V1 and increases in the positive direction till it reaches 0. And the output number T2 in the digital counter is proportional to the RC. So R and C will cancel with each other, T1, T2. So final equation is in this form: V in is equal to V reference T1 by T2. T1 is measured, T1 is known, T2 is measured, and you will get in terms of T1 and T2 the output, and output is. So dual, first you have a fixed time, but depending upon the input voltage, whatever you applied, if you applied this much voltage, you will get this much voltage generated. If you applied this much voltage, you will get less voltage. And accordingly, the T2 will be smaller here, T2 will be larger here, depending upon from which voltage you want to go to 0. And this ramp is generated. These side ramps will be parallel to this, and this side ramps will be up to time T1 they will go. Right? And that is how the diagram clearly explains how input is proportional to the digital output produced. Now analog to digital converter using ADC 0808. Up to this we use different circuits to convert analog signal into digital. Here we introduce another new circuit to convert analog signal into digital using ADC 0808. Other circuits are used for faster or slower conversion. For the same application, we use different basic circuits to make this analog to digital converter. A comparator, a ADC 0 to 5 volts, clock, and circuit, a counter, and DAC. So this is the block of 0804. This is the IC with so many pins, and this is the IC with so many pins. The resistance are there, there are outputs indicated here, and the clock pulses are generated and applied. So clock has to be applied, and accordingly output digital 8-bit output is available. Here we see that there is a IC ADC IC 0804. This single IC contains so many pins, and their output is available at 8 pins, and to the output we have connected with resistance some LED diodes as indicator. The same circuit is shown over here. It has been fabricated by our student Snehal Vatalia, and the output is also shown here. So this experiment has been conducted in the department using this IC. However, if this is a 8-bit IC, and therefore it requires 256 comparators if we want to make a simultaneous conversion. Now In the next further slides, you will see how a gigantic huge circuit is required if you want to make even a 4-bit conversion, and therefore 8-bit conversion physically is not possible unless and until you have all the circuit on a single chip. Here a comparator to binary converter, this circuit is being shown over here, and you can see how gigantic this circuit becomes. These are not gates, these are AND gates, these are NOR gates, and these are output indicators. This is LSB, lowest significant bit, and this is the MSB, most significant bit. This is a 4-bit output, okay, digital output. And this circuit, you can see how gigantic it is, and we are trying to make a 4-bit converter. Okay, so these are the 4-bit outputs of the uh, analog to digital converter. Now we see NOT gates, AND gates, NOR gates. So 3 different types of gates are being used, and all these NOT gates are having one input. That's okay. So they are inverters basically. And AND gates, there is a 2 input gate here, there is a 2 input gate here, there is a 2 input gate here, 2 input gate here. So these are all 2 input gates. In addition, we have got NOR gates. Now this NOR is a 2 input NOR gate, this NOR is a 4 input NOR gate, this NOR is a 8 input NOR gate. So these NOR gates are also, their inputs are also increasing. So a gigantic 3 different types of gates with different types of inputs, numbers and outputs. So such a kind of huge circuitry is to be made. In manufacturing process, when millions of things are made, it is easier to work with one single thing. So always we use NOR or NAND gates, which are called universal gates. So using those gates, we can produce anything else. So when you want to go for mass manufacturing, you will not use different kinds of gates. So these are just a schematic diagram. Actually, you can use these different gates and make the circuitry, but it will be very complicated. It is very difficult to make this circuit, and it will be very difficult to work also. You may not get a 8 input NOR gate. You may get 2 input or 3 input. As soon as your input increases, the cost of the chip increases very fast, because cost depends upon the number of pins available to you. So a 2 input and 1 output minimum. So 3 pins for one gate. So you can have 4 gates in a 4 into 3 is 12, and 2 for power supply. So 14 pin IC will give you 4 gates of 2 input, but 3 input the gates will reduce, and if you want a 6 input gate, there will be only one single gate. So you have to increase the number of pins. As soon as you increase the number of pins, the cost will shoot up like anything. Now we are having 40 pin ICs also, which are microcontroller ICs, but they are costing 50 rupees. And these small gates, if you go on spending 50 rupees, you will be making such a loss that the industry cannot sustain at all. So now you try to see what is happening over here. Inputs are available here, they are given here, and a gigantic circuitry is made. For LSB1 you need this huge gate because 8 inputs are there. For LSB2 we need smaller. For LSB3 still smaller circuitry, and C8 output is directly given to the MSB. So this gigantic circuit is just given for an example how difficult it becomes as you increase the number of bits for conversion. Dear friends, up till now we have tried to see different parameters and definitions of ADCs and DACs. This is yet another diagram which makes us very easily and comfortably understand the process of signal conversion from analog to digital. What is the difficulty, and it gives us one more parameter of study, the speed of conversion and the accuracy of conversion. This red line corresponds to the analog input voltage which is continuously varying. And this same graph we have reproduced 3 times. And what is on the x-axis? Y-axis. Y-axis is the voltage of the analog voltage, continuously varying. And on the x-axis is the time axis. But x-axis actually the time is continuous, but in order to consider a particular value of analog voltage, we have to keep this voltage constant and apply it to the circuitry which I have shown you just now. That circuitry and ICs will take certain time to convert it into digital form, and that digital output will be available to us. So it will take a finite non-zero time. So if you are taking a measurement at this point in time, you sample and hold this circuit constant input and convert it into a number, digital number. Then you take a sample here, a sample here, sample here, and make the measurement. Then you have got this information, this information. In between you don't have any measurement. So you will have to join them as straight lines. So this green line will be the joining, and that will say you have converted analog into digital. So this green line is a very poor representation of this red line. So anyone can say you have missed all this information, your accuracy is not good, this is rubbish, you throw this. So what people will say, I want a better conversion. And here we have assumed that conversion is accurate. No, we have not talked about any error on the y-axis. In spite of that, this is the story. Infinite resolution. Now, if I take more samples, instead of these samples so far away, I have taken 2 more samples in between. So what happens? I got more readings. So naturally my error has reduced. Now it is looking something like red line. But still I am not happy. This information is gone, this information is gone. So there are peaks and some errors. So I am not very happy with this. So for a better conversion, let me take more samples. So if I take more samples, I increase by 1 more sample, then I will get something reasonable, but still there is error. That means I have to sample faster and faster. A faster and faster sample, if I talk about 8-bit accuracy, one sample requires 8 bits. So 8, if you are working at 1 megahertz, you will require 8 microseconds. Okay, so you cannot take samples earlier. So after 8 microseconds plus gate time and all that, let's assume it is 0, even then 8 microseconds will be the time between 2 samples if you are working at 1 megahertz. Now, if you are working at 1000 megahertz, that is 1 gigahertz, your accuracy will improve. You can take faster and faster samples and make it more and more accurate. So your analog and digital will be better. So you need more samples, that means you need to sample more, you need to work at higher and higher frequencies, you need faster and faster clocks, and your ICs etc. should also respond fast. So you need faster and faster ICs also, faster and faster transistors. So your ordinary BJT will not work, you will need CMOS transistors, you will need new technology, you will need nanomaterials and maybe much better materials. So bandwidth or the frequency of operation is now getting very important, and that is required when you talk about speed of sampling and speed of conversion. Here the word time is becoming important, and you have to worry about the speed of your device's response.